Alright gang, here we go. This is for Chem 1 Unit 11, Part 4, talking about molality. This should also be a pretty quick unit or video here, just kind of quickly going over. This is the other big concentration unit that chemists use, and we'll kind of talk about why chemists use it versus molarity sometimes, and kind of what its general purpose is for. In the next couple of videos after this one in this unit, we'll talk more about specific cases and actually apply the molality. But right now we're just kind of getting used to the what it is, how does it work kind of thing. All right, so molality is a unit of concentration. Again, it's a way of keeping track of how much solute is dissolved in your solvent. Okay, now molality is always written with a lowercase italicized m. All right, lowercase italicized. Remember molarity, okay, molarity was like this, and it was in a capital M. All right, so lower cases. So that's what I said when I meant a couple of videos ago when I told you to watch out for those capital M's versus lowercase m's. They mean different things. Here we go. All right, now molarity, just to recap here, was defined as the moles of solute divided by the liters of solution. All right. So essentially with molarity, we were saying that our concentration, we had so many moles of our solute divided by the liters of our total solution. Okay, now molality is slightly different. It's still moles of solute on top, but notice the denominator now is kilograms of solvent. All right, so it's not the kilograms of the whole solution. Up here with molarity, it was the volume of the whole solution. Now we're only caring about the kilograms of the solvent. Okay, so that's the biggest thing that most students mess up when they're doing molality problems is they'll do the kilograms of the whole solution instead of just the solvent. All right. So make sure you keep track of the difference between those two. Now let's just talk about real quick, why would you use kilograms instead of volume? They're both about equally easy to measure. You can take your solution, put it in a graduated cylinder or something, and figure out what the volume is. You could also just take your solution, stick it on a balance, and subtract out the glassware it's in, and you can figure out what the mass of it is. Now the big difference, if you think about water real quick, we've talked extensively about water, and so if you get water really close to the freezing point, what starts to happen to that liquid water? Well, you should know that the hydrogen bonds start taking over, and your water will start to expand. It becomes less dense. Okay, and so you could imagine that would imply that your molarity, if your volume is getting bigger and bigger, then that would imply that your molarity would be going down because your denominator would be getting bigger and bigger, so you'd be dividing by a bigger number, and your molarity would be going down. But really, your concentration wouldn't be changing so much. Okay, and so what occurs is our molarity can actually change drastically when we're close to either the freezing or boiling point of whatever our solvent is. 99% of the time, the solvent is water. It's the universal solvent. So most of the time, we care about when we're really close to 0 degrees Celsius or 100 degrees Celsius. But really, the freezing point, boiling point changes, or sorry, the density of your solvent can change pretty dramatically when you're close to those phase changes. All right, whereas your mass does not. Okay, so if you have 1 kilogram of liquid water and you start to freeze it, and then it freezes, it's going to be taking up more space. Its volume is going to increase, but you take that chunk of ice and you stick it on a balance, and it's still only going to weigh 1 kilogram. So your molality doesn't change when you are close to a phase change, which is the real key. All right, and we'll talk all about what kind of things does this impact in the next video. All right, so the way you use molality is just this sentence down here. So it says a 2.00 lowercase italicized m, okay, NaCl. So that's implying that it's a 2 molal sodium chloride solution. All right, that's how you would read that. A 2 molal sodium chloride solution refers to 2 moles of salt and 1 kilogram of water. All right, pretty easy. Very similar to molarity. You just got to keep track of that volume of solution versus kilograms of solvent. All right, let's do a quick practice problem. Should be pretty easy. All right, it says how many grams of potassium iodide must be dissolved in 500 grams of water to produce a 0.060 molal potassium iodide solution. All right, so we know our molality, all right, that's what my molality symbol looks like, is equal to moles of solute. In this case, our solute is Ki, over kilograms of our solvent. In this case, our kilograms is water. And so we need to find, it asks for mass of potassium iodide. So first we're going to have moles of potassium iodide. So that means if we rearrange this formula, that means our moles of potassium iodide would be equal to our molality times the kilograms of H2O. Okay, all right, so molality was 0.060 molal, okay, and then the mass of water in kilograms divided by 1,000, so this becomes 0.5000 kilograms. All right, so now we have the moles of potassium iodide. All right, so 0.06 times 0.5, we get 0.03. I guess I could have done that in my head. Oh well, better safe than sorry, right? And so this is the moles of potassium iodide. Okay, now we got to convert that into grams of potassium iodide. So that means we need the molar mass of potassium iodide. Now I don't have iodine's periodic or molar mass, atomic mass memorized. All right, so so I had to look it up real quick. So anyway, so that means we need the molar mass of potassium iodide. So K and I. Potassium is 39.10. Iodine is 126.90. All right, so we'll add those guys up. 39.1 plus 126.9. All right, and I get 166. 166.00 grams per mole. So now we'll convert our 0.030 moles of potassium iodide into mass, because that's what it asked for. So we'll put moles in the bottom, grams in the top. For every 1 mole, we have 166.00 grams. So we take our 0.03 times the 166, and we get 4.98. But this guy only had 2 sig figs, so really it just becomes 5.0 grams potassium iodide. So in order to make our solution, all right, we'd measure out 5 grams of potassium iodide and half a kilogram of water, mix them up, and you're done. Okay, and that's it. So next time we'll talk all about colligative properties, and colligative properties tie directly into molality. So do your practice problems. Pretty easy. Let me know if you have any questions, and I'll see you on the flip side.